All right, so today for the exam one lab, I chose to work on problem set 3. Gotta change it to the pen. We're gonna be talking about the how to get the average atomic mass of an element that has 3 isotopes. So when they mean by when an element has 3 isotopes, they mean like the same element but different neutrons. It has the same protons because the protons are the foundation of the element, so you can't change it. So you see here is an example of carbon, how it has 12 protons and neutrons, 13 protons and neutrons, 14 protons and neutrons. They're the same element, but just different neutrons. And you see the percentage here, how it says that there's different varieties of abundance per element. 12C has 98.9% on Earth where you can find. 13C only has 1.1%, and 14 has less than 1%. And so how we're going to find the average atomic mass of this hypothetical, I don't think it's a hypothetical because I think I'll be able to find it on the periodic table. So we start by turning the percentage into an actual decimal, and you multiply the decimal to the mass of that element. So to start off by going with 15.00 times 0.348 plus the next isotope of the same element to be 16.00, then 0.201, and then lastly 17.00 times 0.451. Now you just input this in the calculator. You can use anything. I'm just gonna use my phone because I should have had my calculator on hand with me. Just a moment. $15.00, then the 0.348 plus 16.00 times 0.201, close, then plus 17.00 times 0.451. So in total, for all of them, it's equal to 16.103, but the lowest you just round it to 16.1. That's the average atomic mass unit of those 3 isotopes. I think this, let's see. So 16 on the periodic table, it would be I don't know how that would work actually. But that's how you'd find the atomic mass unit of this hypothetical element. And now to find the that's the answer to number 5. So number 5 is 16.1 AMU, because it's asking us to determine the average atomic mass of that element. And the average of that element is 16.1 AMU. And now we go on to number 6 of the same problem set 3. And there we would find, it's asking us if you had 72.4 grams of the above element, how many atoms would be present? So we start off by what we're given, which is the 72.4 grams. That's how you always start your differential analysis, with always with what you have, never with what you're trying to get it to. You put 72.4 grams. It's always nice to have a path to where you're trying to go to. So we're trying to go from grams to atoms. And we need to find like the middleman. So from grams, we will find mole. Mole to atoms. Mole is like a mole is like a one-stop shop type for everything. To be able to connect everything together neatly, so that there won't be any issues. So it's like let's say, sorry. So you're trying to go. Let's say you're trying to go from. Let's say I had like 32 grams of oxygen, and I'm trying to turn it into. Well, let's write it down. Let's say I had 32 grams of oxygen, and I'm trying to see how many atoms I have of that. So we go by how many oxygen, how many grams are in one atom of oxygen. Well, gram and atomic mass unit are the same thing, so AMU equals to grams. So whenever you find on the oxygen on the periodic table, the atomic weight is 16.00. That's what you put, 16.00 grams mole. One of those is 1 mole of oxygen. And 1 mole of oxygen is 6.022 times 10 to the 23. That's your oxygen atom. And that's how you'll be able to find it. Let me find my calculator real quick, because I need to use that for... Here it is. So with... Sorry. So with 32, put into in the calculator, 32. Well, I like to do it the long way. Putting the 1 divided by 16.00 and then the times of 6. I like to do it the long way because it's just been easier to me. You can do it however you like, but to me, I just like doing the long way. And if you're starting off, it's just better just to put everything into the calculator, just so that there won't be any missteps. So 32, well, open parentheses, 32, close parentheses, and then open parentheses again, 1 divided by 16.00, close parentheses, and then open parentheses again, and then you put the atomic mass unit, which is 6.0. No, I'm sorry, you put the weight of one atom, which is 6.022 times 10 to the 23. And then divided by 1, and close it. So there's 1.2044 times 10 to the 24. That's how you get like the the number of atoms in 32 grams of oxygen Now we're trying to find 72.4 grams of this hypothetical element. I'm trying to solve it. And so now we do the same thing. So the average atomic mass unit of this hypothetical, which we found earlier to be 16.1. So 16.1, like I said, AMU is grams, so AMU is equal to grams. We can turn it into grams. Is 1 mole of this said thing, a said element, and 1 mole is 6.022 times 10 to the 23, which now equals atoms. Let's put into our calculator. 72.4, 1 divided by 16.1, 6.022 to 23 divided by 1. We get 2.708 times 10 to the 24. But the correct sig fig, it's always based on this one. So you get well, not always. It's based to the lowest amount, but since that one's like 3 as well, might as well just call it that. So for multiplication and division, it's always the lowest sig fig. Sig fig means how many important numbers to put into the last answer. So these are, this counts as 1, this counts as 2, this counts as 3. So you only put 1, 2, 3. And so you have to round the 8 to 1. So now it equals, equals 2.71 times 10 to the 24 atoms. I think that's what it asked for. Yeah, that's what it asked for. And that's it for problem set number 3. Thank you.